Thank you for coming.
Thank you, Karen. Well, good morning, everyone. I want to just say that it's a real privilege for me to come here to participate in this program. I'm a latecomer finding out about the program. Once I'm here, I found that there's a lot going on here. So in fact, this title, Bridging the Mesoscale Gap, was not the original title I had thought I was going to talk about. It happened during the Monday, Tuesday organization. So I'm going to confess to you that I'm changing my talk as we go. I had some ideas about what I thought I would talk about, but those are still there. But there are other things I thought maybe even more interesting. So let me begin by thinking back a few years and show you a picture. So it's 1997. This picture is actually, I think Jim will recognize this very well, even though he wasn't in the picture at the time. But he is the guy who should be in the picture. In fact, he is in the picture, as I would try to indicate. So this is like, looking back, a little retrospective. 97, 17 some years ago. A group of characters. I think I was going to ask you, is this Michael Falk by any chance? You all know? Is this Michael Falk by any chance? This is Robin Salinger, and this worked with you. In fact, these are your people. Some of you know, Nasser Ghanim, UCLA. There are some David Pettifor over here from Oxford. Rob Phillips, Caltech now. Number of people who are all on the scene. And the topic that brought us together was dislocations and plasticity. Not quite the theme at this workshop, but not that far away either, right? So this is a group of people that 17 some years ago were here. This is the courtyard before the renovation. This is on the back. And Tim Kexeris and I were actually brought together by Jim. Jim asked us if we would actually run this long program. Jim, I don't know if you remember, the name of the program is called Methods of Materials Research.
I was interested in that.
Right, and I would, the statement I want to make right here now, it were not for Jim, I don't think the condensed matter folks and the glass folks and all the other folks would have the same kind of presence now. It's really, Jim is the one who sort of got it all started, and he's still here. That's the marvelous thing, and we can still ask him questions, have him give comments. So, there is a continuity here that's interesting for me. What's interesting also is that I realize, in one way or the other, we're all trying to connect the dots. It's up to you to pick what the dots you want to connect. Okay, so in some sense, the connecting the dots is bridging the mesoscale gap. It's also equivalent to a number of things that we all know about. We use different terms for. So in some sense, I'm trying to say that we're still at it. These are now different dots. 17 years ago, we were talking a lot about piles, barrier, pile stress, how do you move a single dislocation, and crack tip plasticity, what happens, what is the plasticity at the crack tip, which is quite different from plasticity anywhere else, because you have a crack. And also when you have dislocation, you have a core. The plasticity of a dislocation with a core has two parts. It has the core part, it has the continuum part. So again, it's linking the scales from the atomistic, the core part, the inner part, the local field part, to the far field part, which is the macro part, which is the part that does scaling and so on. So there's always this dichotomy, this tension between what's local. You need a mechanism to trigger things off. But once it's triggered, then it has to respond in some constraints, which could be far field, near field like. So there are all these issues, not exactly the same way that we're thinking now. They're sort of lurking, and people address them. Very good people who came, and they go away, and new sets of people came. And I don't know. I don't see Shrikant here. There's this glass program that Mark was involved in, and it was a few years ago. some of the issues are also there too. I would propose, and in fact, Jim was the one who kept asking this group. He said, "You know, you're only talking about crystal plasticity, although it's not mentioned. This location implies crystalline materials. So you're talking about crystal plasticity, but there's plasticity elsewhere too, amorphous plasticity. Rubber also cracks if there are no dislocations. And how do you think about that?" And so I think, you know, we can trace that to the STZs that eventually various people will talk about. And we're starting to broaden more and more, going from crystalline objects to amorphous objects, and sometimes there are things that go from crystalline to amorphous, amorphous to crystalline, you know, various transformations. So things beginning to get broader and broader, but I am thinking that we're still all trying to reach out and talk across our own disciplines. And it's in that spirit that I come and try to sort of enjoy myself and say a few words. MIT is a very busy place. It's very active. And we do have, you know, very broad discussions, but they typically are seminar type. You talk to someone for a day or two, but we don't have a sort of a center like KITP where this kind of discussions are really going on in depth, in breadth, and also in some kind of continuity, because there are various organizers, previous organizers. In particular, Jim is a super organizer. He's been here. Even though he doesn't remember everything, we don't expect him to, but on the other hand, he does see the landscape a lot better than many of us, right? And let's face it. So from time to time, Jim needs to sort of kick in here and throw in what he thinks things is relevant. So that's just my very brief, sort of long-winded introduction, brief and long-winded, to say how happy I am to be here watching things, trying to learn a few things, and ask some questions. Okay. So that, having said that, then let me now go to this connecting the dots. Last few years, I've been looking at problems from my own perspective, and I have to confess, you know, I'm not very good in following literature. I don't go to a lot of conferences. So there are a lot of things going on in the community I'm not aware of, and I sort of rediscovered them late, typically late. But nonetheless, I see some really interesting thing going on. So I would propose that what I do with you now in the next, half hour or so, is to go through an example of connecting the dots. Okay, you can talk sort of generally, but there's nothing like a specific example to sort of focus what we mean by some of the ideas that we're tossing back and forth. And then I must say that it's an amazing serendipity that last week or so I found out Jim has been connecting his own dots all along, of course. And he's got bigger dots and he connects them in different ways. But nonetheless, we're going the same direction. I hope I'm right. And it's for him to say what he thinks. And so this reminds me that there's going to be a set of Jim Langer talks, not next week, but the week of October 13th. I understand Jim is scheduled to talk on Thursday and Friday.
Yeah. Look, I'm still uncomfortable about talking so much. I don't mind doing it, but
you can make it short.
I really enjoy listening to other people.
Okay, then you can. So I pass the buck to you, and you can pass the buck to someone else, and just say you what.
I'm sure, Karen, if there are other people that really need to be talking in those slots.
No, I think this will fit perfectly because that week is going to be all on these same questions. This will be beautiful. I think this will fit really well. Yeah.
I just don't want anybody to think that I came in and said, I'm going to give
Oh, no way. No way.
Jim, if that happens, you can just, first of all, as you know, all these talks, they all start out and then the audience jump up and beat up on the speaker.
I think that discussion should happen offline.
Yeah, right. So, everybody knows the protocol.
No. I'm just saying, I don't think that discussion should be happening here.
Let's hear the talk.
Listen to you.
Okay, so we already, see, the audience already is saying,
Come to the quick.
Show me the beef. You see, there are people who want the beef. Other people are more relaxed. They say, I've seen some. Anyway, I'm not going to keep you longer than I'm supposed to. So please rest assured, after my primary example, this is actually why I call this a primary example. After this little discussion I hope to lead on the superfluid liquid, I hope to sort of sit back and let you people fight it out and ask questions. And some of you will help me answer questions. Some of you will be on the attack side, some of you will be on the defense side, and I'll sort of step out of the way. Okay. Now, if you want more, if this makes sense, and I have a few more additional examples. Like I said, last few years, I've become aware that there are a lot of nice problems out there, and very, very difficult problems. Each one is just a grand challenge problem, horrendously difficult. And yet, beneath all that complexity, there is lurking some common issues that I think we can grapple with. So if you want more additional things like, what does superfluid liquid have to do with yielding? How does it have to do with creep? What does it have to do with stress corrosion cracking? And even what does it have to do with something as boring as cement? I can take up the rest of the time and get into some of those things. But those are just more talks. I think in terms of the best example that I know, and I know there are experts in the audience who could easily come in and contribute, is we take the example of this superfluid liquid example, okay? And then at the end, if there is still a little time, I want to come back and say something about why all this anything has anything to do with closing the gap, bridging the gap. There is actually, in my view, not quite a gap. It used to be a gap, and now more and more people become aware of it out there, and it's become a frontier. So a frontier, by definition, is still sparsely populated, a few people, but there are things out there that's probably worth discovery, worth settling in on, so on. So anyway, I could sort of finish with that, and that's when I expect we run out of time. But by all means, I'm not going to be upset if we don't get to the whole thing. So feel free to. I know you will. Even if I say feel free, I know you will, and I'm going to have to just tell you that if you ask detailed questions, I'd like to take you offline. If it's mostly technical details, but if it's sort of conceptual issues, by all means, and if more people can discuss, by all means, let's do it here, because let's grab the moment while we can. But if some of you are interested in some of these things in specific details, like how do you work this, how do you work that, frankly, I don't remember some of them, and it's not probably appropriate to talk about now. So let me just move along and tell you what I mean. It's actually really simple. Well, this is the problem. This is the problem that I think we all know. And again, I'm looking to see if the tree is going to come, because the tree knows a lot about this. Jim knows a lot about this. Mark knows a lot about this. Many of you, because this is a famous problem. It's not my problem. It's a famous problem. It was, started out. I guess the plot like this is sometimes called the angel plot, sort of named after Austin, who did it in 1980 something. And he took a lot of data. There's a lot more data. The angel plot has a lot more data on the viscosity of glass-forming liquids. So if you're plotting viscosity here over many orders of magnitude, this is now about 20 orders of magnitude in real units, all data now. All right. So there's no scaling here on this, but over here on the y-axis, on the x-axis, instead of plotting the temperature, Austin decided to plot Tg, which I'll define, over T, so 1 over the temperature. So as you go to lower temperature, you're actually moving to the right. So the high temperature, so the room temperature viscosity, say of waters, 10 to minus 5, 10 to minus 4, minus 5 poise, is down here. It's very low. So this is high. This is a low viscosity regime, a high temperature regime, so 1 over the temperature now. And then as you quench the system down, it doesn't crystallize, so it stays it's vitrified, so at some point it turns into what you call a glass. And what you know is that the viscosity, we can talk about other properties of this vitrified liquid. But if you just measure viscosity shows us very dramatic behavior. And this is a behavior that I think we should sort of focus on for quite a while, because I see this sort of behavior in this following sense that I'm going to discuss. I see this in many other phenomena, not necessarily viscosity. It could be useless. It could be swelling of material under irradiation, and I have examples of that, and so on. So what you see now, coming back to viscosity, the reason there is a question here is that everybody says, okay, that's what the data. It looks reasonable enough. When you have a liquid at high temperature, it has viscosity of a certain value, and they're pretty low viscosity, and they gradually they decrease as you cool to lower temperature. The fluid become more and more viscous. That's all it's saying here. So this region is simple. The low viscosity, this one can be actually understood very simply in terms of the ordinary transport theory. Collisions, Boltzmann equation, for example, Boltzmann and Scott equation, you want to get a little more higher in density and so on. So the traditional statistical mechanics of transport phenomena can handle this region very well. But then when you see what happens is that when you go quench to lower temperature, viscosity at some point shoots up. Remember now, we're plotting log here. So this is the Arrhenius. This is like what we might call the normal behavior. And at this point, this is highly super Arrhenius, and viscosity just rises very, very steeply. And then, depending on how you look at the data, you might say, this portion, again, it becomes Arrhenius. So you go from Arrhenius to non-Arrhenius, or super Arrhenius to non-Arrhenius. So clearly there's some kind of a crossover. Angel coined this two regimes, Arrhenius versus non-Arrhenius. He calls this the strong behavior, namely is Arrhenius, and the highly non-Arrhenius he calls the fragile. Now here's a set of data that shows that they all, these are different molecular compounds like glycerol or all kinds of glass-forming liquids. But there's also another very well-known network glass former, the silica, which doesn't show this behavior at all. It shows over a fairly extended range of temperatures, which I don't show you here. It's completely Arrhenius. So Angel, in his plot, puts the word strong here and puts the word fragile here. And that word fragile has stuck. People are starting to talk about fragility of the system. So when you start talking about what is the nature of the glass transition, and here I'm glad Sri just walked in, and so he knows, he can tell us, and I think he has more recent, because he's in constant touch with Austin and so on. So he can sort of brief us on what is the current understanding of fragility. And I know there have been workshops held in Denmark, like Jeff Dyer. So fragility is a big issue. It's already here, okay? So in some sense, if we had managed to have some understanding what is the underlying molecular processes that give rise to this, then we are actually part of the discussion of fragility and the nature of the glass transition. And I think to the outside world, as we know, there was this quote of T.W. Anderson, mid-90s. He said, glass transition is one of the most challenging problems we can talk about. So in some sense, there is a perception of deep mystery, a deep phenomenon, deep physical processes, physical principles going on with this transition here, okay? So that's the problem. Now the question I want to ask today in the next 10, 15 minutes is that can we come up with a sort of a molecular level understanding of what's going on? By that I mean no fitting, and just go at it from what we know about what must be going on when you take a liquid in the liquid state and start to quench it below the freezing point, but quench it quick enough so it doesn't freeze. Okay, so how far can you go with hands off on the fitting? And this means, for those of you who know a lot about liquids, everybody says, oh, there's this Volcker-Focher law. So Volcker-Focher law is empirical. That's not in the spirit that I want to talk about. So I'm not allowed to use Volcker-Focher, even though I know about it, even though I know it will describe something. It may give some kind of a power law, behavior, what have you. The intent here is to sort of go at it from a sort of a bottom-up approach, molecular approach. Start out with interatomic potentials, go as far as you can, and then do whatever else you need. Eventually, but basically come up with a sort of a calculation that gives you this behavior. Well, that's what I want to tell you. We've tried, we managed to do one such calculation, and these points, these color symbols here, are the results of a calculation along the lines that I'm going to describe to you. No fitting, and but it's not a complete, the kind of self-contained calculation that you like to see. There are things that we have to do in order to sort of get to where we are, and this is for you now to critique whether this is kosher or this is not kosher. But nonetheless, we have to do those things, otherwise we don't get what we get here. That's not to say that this is the only way to get it. That's just to say that we managed to get it this way, and we think there are other people who can probably do better, but this is what we had to put together in order to arrive at this curve. Okay, so the discussion is what does it take to get a curve like this without the fitting that would somehow exhibit this kind of fundamental behavior going from a strong at high temperature, a radius behavior, to a fragile, and at some point there is discussion about second. If you call this the strong to fragile a crossover, there's actually talk about second crossover, because you can go to lower temperature. Okay? Now, so this reminds me to define for you what is TG. TG is actually a sort of a convenient property to normalize. It's like a scaling parameter, if you like. So TG, in this particular context, is that temperature at which the liquid has a viscosity of 10 to the 13 points. So if I have a liquid that has a viscosity curve like that, let's say, I apply viscosity as a function of temperature, and as I go to lower temperature, this viscosity goes up, and at the temperature where the viscosity has that value, magic value of 10 to the 13 poise, or 10 to the 12 pascals per second, there's a factor of 10 between poise and pascals per second. Okay? So 10 to the 12 here, I call that particular temperature TG for that liquid. So each system has its own TG. All right. Okay. Now let me also say right now that this TG is purely a convention within the community. Other people who only look at structure don't use TG according to the viscosity. They use TG according to whether or not the radial distribution function has a second peak. So if you cool the liquid down, the radial distribution function, the second nearest neighborhood peak, all of a sudden splits. Okay, so there are other sort of measures, indications of some kind of a transition. Not really a transition in the phase transition sense, but this glass transition. There are other measures, other ways. And people who do scattering experiments will say, well, I don't necessarily measure GOR, although you can get it out of the data. I don't measure viscosity. I measure diffraction pattern. So I can measure, let's say I can take a liquid, I can measure the diffraction pattern of the liquid, and I see rings, the so-called Debye-Scherer rings. And if I start to quench this liquid, at some point, the liquid crystallizes, and I know that happens because I see black spots. Right? So if you do spectroscopy, you do diffraction measurement, you have another way of defining whether you have a crystal, you have a glass. If you have device shear rings, you have black spots. But the problem is that when they do this kind of experiments, they see both. They see the rings, and inside the rings they see remnants. So this means, it's not one or the other. It's not a sharp transition. So that's why there's all this discussion. The glass transition is not the transition that we know about in terms of melting and so on, critical phenomena. Nonetheless, it's there, and so various people do what they can. But for us, I propose that we just simply focus on this very sort of dramatic behavior of going from very gentle increase with your driving force with your state variable. And here I see Boo Boo has an example from her slides where
I don't think it's the same, but
yeah. And so here we already have a little.
You have a log plot. I can show you a log plot.
Yeah.
It's not as sharp as this.
Right. I mean, this is only an example, by the way. All right. So there are other people who do linear plots. This is a log 1 over t. Is not okay. So there are different variables, but I think that the underlying question, nonetheless, is still a good question. Namely, if you see something in whatever you call it, my question to you is that, do you understand it? If the answer is you would like to understand it, then we're on the same page. I don't mean to say that everything has to be like this. That's expecting too much. I like to have the license of being able to talk about different state variables, not necessarily the temperature. I could talk about the applied stress as an external driving force. Packing fraction will be another state variable. You can have the different ones, but the point is that when you start to do something to the system quickly, and this is where the rate effect comes, the system feels jammed, frustrated, confined, all these different words. It's unable to do certain things that you would normally do. So rate has everything to do. That's why once you get into this, one of the big problems in the glass community is, what's the quench rate? Well, quench rate is whatever you can do in the laboratory, for example. And therein lies a big difference between people who do simulation of glass transition and people who actually talk about the measurements. When you do simulation, you quench the system like crazy, 10 to the 7 degrees per second. That's a huge quench rate. Nobody does that in the laboratory. And that's reflected in this as well, because you might say, well, not that many people care about viscosity, although I would argue otherwise. But you just remember that the viscosity can be expressed as the product of a shear stress and a relaxation time. Okay, that's dimension it. It makes sense physically because viscosity is transfer of momentum shear stress. When this thing goes through 10 orders of magnitude, the shear stress doesn't change that much. When you take a liquid, high frequency shear stress, liquid has high frequency shear, no zero frequency shear stress. To a glass, the shear stress may change by 2 orders of magnitude. And if you have 10 or 12 orders of magnitude change here, you have 9 orders of change of magnitude in the relaxation time. So that's another way to think about this. Glass really means glass dynamics. Viscosity really means glass dynamics. So you have a system due to whatever collisional process going on that has very short relaxation time. All of a sudden, when you lower the temperature, the relaxation time goes through the roof. And this is people call this critical slowing down relaxation. What is going on there? The same question, if you can explain why the relaxation time goes, and people measure dielectric relaxation too, so you don't need the viscosity. nonetheless, you have to have an understanding of what's going on in your system as you sort of lower the temperature a little bit, not many degrees, but the relaxation time is changing very. What's going on? Okay. You will find that at the end we don't really know anything more than what we can now say is, I believe, and this I'm here now at the mercy of people who like Shell Street. You can say that I believe that one of the ways to understand the fragility is to go back and think about the underlying energy landscape. In other words, when you quench the liquid, the underlying energy landscape of the liquid can be very sensitive to the function, to the temperature to which you quench. If you quench a high temperature, the energy landscape may be very smooth and not very interesting. But if you quench below a certain transitional temperature, you all of a sudden now generate a very, very different energy landscape, which can be very, very deep, very, very rough. So if you are trying to, as you explore viscosity, I mean, after all, this is a transport phenomenon. So you talk about mobility, you talk about transfer. As you explore this energy landscape, it's not enough to just think about where are the minima, but you now need to go to saddles. You now need to get out of the deep ones and go to the next deep ones and keep on going. It's not just a single process. Once you're done with that, that's it. So this is the challenge to the transport. So now you have to sort of generate various trajectories in your transition state pathway scenario on those rough energy landscapes that you have created. Therefore, if you want to calculate the viscosity at this temperature, fairly high temperature, or at this temperature, fairly low temperature, you can bet that you better use very, very different underlying energy landscape, because that's what system is doing.
Okay.
Yes?
Could you tell us more about the effect of the quench rate on this actual curve? Do you move the transition or?
Yeah, well, if I can postpone that, maybe Shot Street can answer the effect of the quench rate on the on viscosity.
Viscosity?
Yes.
Well, I mean, the glass transition happens at different temperatures.
Okay, so you move this curve. That's
You
right.
do, yeah.
No, not in this way, right?
If you
Scale this
normalize,
way,
okay.
nothing changes.
Yeah,
Yeah.
as easy as a scale.
Okay.
Right. So effectively, you would
As long as you're in equilibrium.
sort of, I mean, if I were to translate what happens on this diagram, the data would begin to look more and more strong. the
Yes.
faster you quench.
Okay. Yeah.
But wait a minute.
Not if you're in equilibrium in the supercooled liquid, right?
This is all supposed to be equilibrium behavior.
Right. No, so
Whatever that
So,
means.
Yeah, whatever that is. That's exactly right.
Well,
Yeah.
in principle, you waited as long as you have to wait. Anyway, up in that upper right corner, you have to wait much longer than the attention span of a graduate student, to say nothing of his professor, to equilibrate. But in principle, these are supposed to be equilibrium properties of the measure.
No, Jim, the point is, depending on how much you weight it, you have a different PG, which is...
Oh, that's
which
true,
is-
but how far, in other words,
steady
if you've not let the system, in other words, age at a temperature doesn't last, temperature
So I think that would remind me to say that this 10 to the 13 poise to define TG is not an accident. People in the business who actually in glass actually know that at that value 10 to the 13, if you put in reasonable value for 12, you have a relaxation time of about 100 seconds. That's a working range of glass technology. Okay, that's why they're interested in viscosity of that magnitude, because in the laboratory, that is the kind of viscosity that they can blow the glass and wait for it. They work with it, they can form it. So 100 seconds, all right, 100 seconds for the relaxation time. Now, you can ask yourself, is that equilibrium? It's not. It depends on what the internal relaxation is. So, well, that's a discussion. And following that whether it's thermodynamic, non-thermodynamic quench, or kinetically trap. That's all that is to be done, but I still come back to that. Keep that in mind. Let's talk about how we can calculate this. So if you don't mind, I'll just continue. So, yeah. To me, there are three steps that I can think of to try to put together a curve without fitting. Okay? The first step is to take advantage of the fact that we all know that as you quench the system down, you're going to work with a quenched liquid, which has a different underlying energy landscape. And this is the idea of the inherent structure that was put forth by people like Frank Stillinger. And Shastri here is the house expert on inherent structure. So anybody should talk about that. All right. Now, Stillinger was at Bell Labs working with Tom Weber, also at Bell Labs, and they were one of the forerunners of using MD to probe silicon, for example, and also they came up with a three-body potential for silicon, but along the way they're interested in glasses. Okay, so you run, basically what you do is you take a liquid, you have intertwining potential. This is so no fitting is required. So in this case, let's say there's something called the Cope-Anderson binary Lennard-Jones potential. It's basically it's soft spheres with different sizes, two different sizes. All right, just think of that because the word polydispersity has been used. And you need the two different sizes so that the system doesn't crystallize. In the early days of ND, we found out that if we use Lennard-Jones potential one size, that potential will always crystallize in FCC. We would like to keep the system from crystallizing, so you use two sides Lennard-Jones, and that makes it more difficult for the particles to find the right thing to crystallize. So we have a potential function, and you can run. I see. Oh yeah, here it is. So if you take your MD simulation at various temperature, equilibrate the system, run it as long as you can, so you're sure you have a liquid. Then during the simulation, at various instances of the simulation, you simply just drop. You do a steepest descent quench. You just do energy minimization. Okay. So imagine you're at some finite temperature, and then during that temperature you save various configurations, and at those configurations you just simply drop down. Like you're a swimmer at the surface of the ocean, and then various parts of the ocean you just drop down to the bottom of the ocean. That's like a steepest descent quench. And then you find out what is the energy landscape on the bottom. Okay? So I think I want to think about that. So what you find is that if you quench down to a high temperature, T, by the way, units is always in. So in this case, this T is in some appropriate unit. The glass transition temperature, this is like just keep in mind, Tg in this means really around 0.37, somewhere down here. All right, that means you can quench at high temperature, not quench, you just simply operate at high temperature. Then you are really in the high temperature, very low viscosity. So you're really here. If you want to think about what's going on down there, you have to go down to a temperature about 0.37. So what's important is to say at high temperature you have a spectrum of energy, very, very broad. So this is very, very broad. And then when you get down to low temperature, you can see now very, very narrow, but very, very low energy. Okay, so that means when you lower the temperature, when you quench at lower and lower temperature, do the steep descent quench, you find, and you measure the energy landscape by an average, you find that you have a high value, which means whatever wells you have, a very shallow well, and it's very easy to go back and forth. You go through this very, very steep change, you drop down to a very low, very deep average value, which means now you're getting very sharp well. And there.
What is this?
I think he said
All of them.
co-bands.
Co-benders.
Co-bands.
All right, this is the standard. Yeah. Okay. So this graph, Shastri knows very, very well. This is the inherent structure, energy.
So just
energy,
a small comment said it's quenched from those temperatures.
That's right.
That's the start.
Down to
The steepest descent quench is not at that temperature, but you start from that temperature and you get the inherent structure.
All right. So this tells you something. If you think of the viscosity calculation as an experiment, as in any experimental protocol, you have to prepare your sample. What kind of glass? You're going to measure viscosity of the glass. You know, the glass depends on what temperature you make it. So you have to prepare a sample. So this is about sample preparation. If I quench to high, not quench, if I go work at high temperature, I have that kind of viscosity. If I want to probe the viscosity in this range, I can quench down to various temperature. It's that temperature that really matters in terms of.
But I still want to get back to this point, and Sri can correct me. Sri, yes, should be listening. That T equal to 5 is an equilibrated system from which you get the inherent structures by quenching. The T equal to 5 is not a quenched system. The T equal to 5 is an MD completely equilibrated system, and then you quench to 0 temperature to get the inherent structures.
So basically, you essentially get rid of the kinetic energy and isolate.
Right, but I'm saying the T equal to
position
5 is
part.
not stuck in any state. It's equilibrated. That's
Yeah, but at high temperature, so.
and at point 4. The assumption is that you're starting from
Yeah.
sampling everything and you're calculating the inherent structures.
So I have a question related to this, which it seems to me that this only works because one has small systems. Because if you have a big system, the thermal contraction that would occur would lead to plastic deformation and not give you a state anything like your initial state. But we can maybe talk about that later. But I think partly this works as long as the system is small enough that you really are getting rid of the kinetic energy and going to some energy state nearby. That's the idea, but I'm not sure it works in the limited large systems.
I don't think there's any problem.
I can show you. We should talk offline about this.
So at low enough densities, you do see mesoscale structure becomes different. But for high densities, which is typically where this kind of a formulation is used, there is no. I mean, you do find the structure of the inherent structures to be significantly different from what we start with. But there is no sort of medium or longer range change.
Could I make a quick comment on this? It's related to earlier questions about the quench rate effect. Experimentally, if you look at how the viscosity is measured, basically you cool the liquid down to a certain temperature. In glass, it's the same thing. You basically warm it up at a different higher temperature. You make sure you have a sufficient time for the system to equilibrate, that they don't change. In that sense, the quench rate is not really into the play, right? Otherwise, you would have history dependence on your viscosity. Right?
No, so I think what Google said is clarification on this. I mean, you do sort of, I mean, you can of course look at out of equilibrium behavior, but unless you sort of specifically say that, it's assumed that the properties of the inherent structure of the properties are the equilibrium properties. So your ensemble is an equilibrium ensemble of liquid structures. But then you're looking at the first one.
Okay, just sort of keep going. Let me say that was step 1. And there are 3 steps here. The step 2 is that if you have prepared your sample, now you can stick in your sample into whatever instrument to measure, and something. The thing you want to measure is what we call transition state pathway. That basically allows you to sort of, even though you prepare the system at a certain temperature, which you know what that temperature is, now you can start to characterize the energy landscape. And you do that, the characterization basically is what we call sampling. So you need some algorithm which allows you to find out how rough is the energy landscape. You need to find out the topography. And so that is what we call step 2. And that is now something that I just want to quickly mention, that there are different techniques. If you only have a single unit process, collision or reaction or something, there are methods like the nudge, so-called nudge elastic band method. You know the initial state, you know the final state of a reaction. You can sort of bound these two and then find out using various nodes or have you to find out what is the reaction pathway, right? So eventually this whole game of finding out how do we get viscosity of that kind of behavior surely has to involve in following how the system sample, whatever temperature it's quenched to. So you quench down to 0.3, 0.4. You may be there, but you don't know what is the underlying temperature. Therefore, you don't know how to get the viscosity for that, right? So to get the information that you need to calculate viscosity, you need to know what are the details of those energy landscapes. And those details, what we might call transition state pathway. I just want to illustrate something. Let's say your system has this kind of energy landscape, and you start out here. Let's say you start out somewhere in the bottom. Now, how efficient is your sampling technique depends on how clever you are in getting this red dot to be able to climb up, go over to a saddle, go to the next nearby one. There are lots and lots of them, right? So you have to somehow have an efficient system that allows you to do this kind of sampling, which means you have to be able to find out or calculate or sample the minimum, the configurations. You have to know where the energy minima are, and between the minima, they're always separated by a saddle point. So there's a high dimension map of the surface of minima and saddles. Okay. How to find that information, which you surely must have in order to get the viscosity. Otherwise, if viscosity is independent of this information, then so viscosity has to depend on the information about how you move on this energy landscape. And I say that over again because the viscosity is a transport property. Right? Transport property implies mobility. So you have to figure out how does the system move on its energy landscape.
You have to remember that this picture you're drawing is a one-dimensional picture, but you're trying to reduce 10 to the 23rd dimensions to this one-dimensional picture. For example, it depends on what direction you actually are going, and you're going to find a saddle point.
Yes.
Okay. Then the question is it really a saddle, or is that the way you're drawing it has sort of one direction in which it's unstable to fall on, that you get up to some place that has zero force, so to speak, in this limit. I have to 16 or 15,000 directions in which it could go from there. And don't you in order to understand the dynamics of the system, don't you really need to understand something about that?
Yes, the answer is yes, but we're all very limited. So I don't. At this point, there are other people who thought about this and who actually have some better answers than I have, and I have to refer you to, the people who actually started this. This is Michele Paranello. His method of so-called metadynamics. Now, Paranello was able to answer part of your question by he did not apply this to all degrees of freedom in the system.
But he also didn't work with glasses, did he?
No, he worked with isomerization of molecules. So that's a much simpler, problem where they know what the collective coordinates are, and they usually tens and not millions and so on. But what we have done is we said, well, we don't know what are the collective coordinates because they come and go, they change. Therefore, we simply just do it to everybody. Of course, it slows us down tremendously, but something is better than nothing was our approach. And by the way, I have to really confess, we didn't do any of this thing with the biggest state-of-the-art computers. We have a very modest budget, and this is all shoestring stuff. So by all means, when it comes to size dependence, somebody mentioned, when it comes to enough statistics, we are very, very weak in that. But at least we have a glimmer of what's going on. And yeah.
No, I think apart from how it's going to work in practice, I think what Jim is asking is just a matter of principle question. Whether a method like this can work in a high-dimensional parameter space. So what meta-dynamics has been developed for and used for is to work with sort of fairly small number of order parameters and to define the energy in that limited space and to sample that efficiently. And there you can see that it might do a good job. So, it's a work in progress. But if you have a very large number of degrees of freedom, there is no hope of sort of defining this bias potential that you need everywhere in configuration space. Because if you could do that kind of sampling, then you have no problem to begin with. So I'm not very optimistic this will work.
But let's see what he's done. I'm waiting to see what's done.
That's good too. That's good. Okay. Yeah. So your cautionary remarks are well taken and not forgotten. Yeah. Okay. So following Boo-Boo's suggestion, so this is a method whereby you can actually walk your way around this energy landscape. And the one nice thing about this method is you don't have to know the final state. You can start out with initial state, and you just simply let the system find its way. It's very efficient in that sense. We have benchmarked it against other systems like dimer method or some our voters. And in the case where we could do something fairly simple, it has worked, but it doesn't mean that it's safe. Okay.
Sorry, just to ask you a question, I can sort of see that this might be a good way of accelerating dynamics, even if I'm not sure about the cost. But my comment was more about whether you can actually get any kind of free energy information.
Okay.
So I don't think maybe you can say more.
Yeah, let's keep that for a later point. In the interest of, let's just say that's done, and around. I said TG is 0.37 for this problem, so we went higher than TG. We went to T equal to 0.5. All right, so this is the energy length. This is what we call the transition state pathway sample using this method. And it doesn't look like anything, right? It's like the stock market.
I don't understand what I'm looking at.
Yes. And this is good because this is my definition of what is transition state pathway good for. It gives me a set of local energy minima. These are the lower points. And each one is connected to a saddle point. Because that's actually how our system...
But I think the question, so this is the energy of the inherent state as a function of time during a simulation at this temperature?
Not time.
Time, as in terms of the what?
Time.
The steps.
It's the number of
just walk. Start walking.
You've taken in your algebra.
Right.
But at this temperature. So I'm taking the inherent structure landscape.
But that's the same
Close
as
to
the
the
time.
exponent.
Right. At that temperature. Because the potential energy landscape itself doesn't have a temperature. You want to
No,
set
but are you doing the potential energy landscape, or are you taking the inherent structures? I guess that
potential energy landscape.
Well, what's the inherent structures like?
Of the inherent structure.
See, what move is made in each step?
Okay, well, Dan, that's a good question. What we do is, let's say, okay, let me say I'm starting out some state I, one of these. I want to somehow cross the saddle point and go to the next one. Okay. Now, if my intention is to go between I and J, which is far away, and then I have some nearby ones to cross first, right? So this like so what move is being made here? Well, we start out with some initial state. We have an algorithm that actually allows us to observe. So we give the system a little bit of energy. We call what Carnella calls energy penalty. And I think the simplest thing that I can use to explain that is that you imagine you're trapped in some fairly deep. You're at the bottom of a cave. Your friend is at the bottom of the cave. You like to let us pull him up. So you don't give him the whole rope so he can climb completely out. You give him a little bit of rope. That's the energy penalty, all right? So that little bit of rope, he can climb higher and look around a little more because he cannot tap, okay? And then you can keep doing that, and you give him a little more, and then he will, at some point, he might even find a ledge somewhere. And then he doesn't go back down anymore. All right? But then if you give him even still more, so every time you give him a little rope, basically what the system does, you allow the system to relax, right? What the system does is to self-organize. It looks around and finds some local foothold. You keep doing that in small steps until at some point when this climber realizes, hey, I'm now at the top, I can now roll over here because you now let me relax. Instead of going back, I can now roll over here. That means now I have activated, I find a new minimum. So this is a whole series of steps, activation and relaxation. You keep doing that, but the relaxation is done in small steps so that the system has some energy to locally organize, but not a lot of energy. And you let the energy to be distributed self-consistent according to interaction potential.
So is there reheating, or you're heating the system, or?
We're giving the system energy, not in kinetic energy, just potential energy.
Just potential energy.
And then you take that away to the next step. There's even such a conjugate gradient method to the phenomenon.
So this is basically an activation relaxation algorithm in smaller steps, and as a result of that, you're able now to climb out from this local minimum to this local minimum, and climb to the next one. You can explore more and more minima. The reason is you don't go back is that you keep those penalty functions. So there is a energy bias against your going back, and this is a big help because in Monte Carlo when you go forward, oftentimes you just go backward, forward, you don't get anywhere, and this doesn't have that problem. But also this means that as you move forward, as you climb out of the energy landscape, the landscape has changed itself. You're always exploring something that's new. Okay, so that anyway, that's what we get to
Sorry, I have a question.
Yeah.
How is the energy penalty implemented? Because you put that if you're very near to this configuration, then you should have a high energy.
Yes, that's a good question.
But there's a distance function.
Yeah.
How do you?
Very good question. So, again, it's up to you. For example, if you are looking at surface diffusion of an atom, right? I want to know how aluminum on one old surface diffuse. I can just simply activate that particular atom because I want to see how it moves. In this case, we don't know where, so we activate everybody. Okay, so, but we can. So it's up to you. Okay. So, now the important thing is that when we have this, not only do we have the trajectory, the pathway in energy here, this minimum, saddle, minimum, saddle. We also know at every one of these points, at the minimum and the saddle, we have the atomic configurations. So if we want, we have to, we can go back and see what physically has changed when I made this jump across this. All right. So that's the information that I think only simulation can give you. The theory cannot give you. Maybe the theory can mimic that. The experiment certainly cannot give you. Okay. So if I may, I better speed forward. There are some interesting aspects here that people are asking, and I'm happy to talk later on. So I'm going to just say a word of digression here. With that data, so we have done now the experiment. Now we want to analyze our experiment. We've done the measurement. We've done the transition state pathway study. Our goal is to calculate the viscosity, right? You can say, all right, let's go back to linear response theory. In transport theory, we know how to calculate viscosity. In the Green-Kubo formulas, and we do a time integral of a stress-stress correlation function. Right? It's all written down, and it works very well with MDE or with anything else you want to do. So now we need a theory that would actually work for the viscosity of the glasses, and that's not so simple because I'll skip this. So now we can try to use linear response to calculate the viscosity, and that's this formula here. This is the Green-Kubo formula. It's a time integral of a shear stress correlation function. And if we know this correlation function, we can then calculate. If you do MD simulation just basically numerically generates this by following MD steps and so on, right? But the problem with MD, and this is one of the issues I want to say, is you can ask me right from the beginning, why not just do MD and be done with it? The problem is MD cannot cover the temperature range for a very simple reason which lies here, all right? Let me just go back and remind you that if you only could do MD and don't do these metadynamics things, you are able to cover the viscosity range, let's say up to here. You will completely miss the fragile behavior. Okay. So this part is no problem. I mean, we could use anything almost, and because we understand the physics. It's really the part that's in here that's in question. So when we start to do linear response to calculate the viscosity, we are aware of the fact that the information that we got this from 2, which we said we could do it anywhere, right? The information is not really necessary because we don't really. The information from 2 is really necessary only in this fragile part, okay? So just please keep that in mind. Later on, I have an alternative story, a heuristic model where we can actually use this information directly. But let me skip that in interest of time. Let me just do with the sort of the more complete calculation, which is this viscosity calculation using the network model. So now, you remember we have done our measurements, and we now have a transition state pathway trajectory, which, as Jim has said, we could have gone other directions, and this is only one of many. Okay, but at least this is one, and so on. And now the question is, how do you use this one? Well, you can imagine you set up a network of nodes in which every one of these nodes is like a local minimum, and it's connected to every other node. So in that sense that you say, well, I have node 1 and node 700 or node 35, and these things are connected, and I know how they're connected. So I have a connectivity map here that tells me what is the transition. So the rate of transfer of momentum, in this case, is the stress, the shear stress. I'm talking about stress transport. So at every node, I can define an inherent, not structure, which means energy, I can define inherent stress. And I imagine I have a node in which the stress is propagating through the node, through the network. That's this transport calculation. Right? That's an equivalent formulation to what green Kukubo is. So we can actually now, we say if someone gives us a transition state pathway trajectory, we can use that and turn that into a set of nodal connectivity, if you like. With that, we can set up a balance equation and actually calculate the viscosity as a set of nodes with transfer.
So does each node correspond to a minimum that is somehow, you have to identify equivalent minimum along that one-dimensional trajectory?
Right. So we solve this. So right now, this is like 3,000. We have 3,000 local minima, therefore 3,000 saddle points. So that means we have a network system of 3,000 nodes. Each one of them is connected because I can tell you what is the activation energy to go from 1 to 3,000, 1 to 150. I have that kind of, so I have a sort of a matrix of 3,000, 3,000. That's the size.
The activation energy is just the barrier.
Exactly. So once we know the barrier, we know.
But how do you know the barrier? Because you know the path you took, but that doesn't mean that there isn't another way to go that would have the lower barrier, right?
Well, this is all we know. This is all we're using. Okay.
So
we're assuming this is representative.
For the nice barrier between them.
Right.
So you use the barrier along that particular trajectory, which...
Now we actually, that seems confining, restricted to you. We actually, later on, we have a sort of an extended formulation where we actually allow take this, but go in other, Jim talked about this one dimension. We can actually go into higher dimension, extending it. Okay. But with every additional thing that you add in, there's always computational cost. Some of it has been done, can be done, and does improve things, but there's nothing dramatic that's totally missing. That's what we know. Okay. So with that said, then you can say, well, all right, if I know the inherent structure, I make the sample preparation, I've done the TSP sampling, and now I have this network model that allows me to calculate the viscosity at any functional temperature for which I have this kind of information. And now let's look at the results, and then that's so. It turns out that we realize that we don't want to calculate the viscosity at any arbitrary temperature, even though we want to cover the viscosity over a certain range of temperature. So we took that range and broke it into 4 separate regions. So this is you remember now, this is the inherent structure. So at high temperature, 1 over T is small. The inherent structure of energy is fairly small, the wall depth is low, and then when you get down to lower temperature, it drops. So we decided to break this temperature range into 4, into 1, 0.5, 0.4, 0.3 temperature. So we use we prepare 4 samples. Okay, we prepare a sample of T equal to 1, and we got the transition state pathway. That's what that one looks like. We prepare another sample, lower temperature of 0.5. We got this green one, another one at 0.4. That's the blue one, and then finally the lowest one, 0.3, and that's this red one. And using this as input, we do green Kubo.
So what is being plotted on the
This one. This is the transition state pathway at that temperature.
So what? Energy at the sample?
Energy as a function of sample, right?
But it seems inconsistent with the distribution of energies on the second column.
You mean here?
Yeah, the 0.3 would seem to have...
0.3 is lower. 0.3 is very, very narrow. And this is what
right,
we
and
have
it
seen.
has very low negative values, and I don't see those negative values on the
Stuff
right.
over on 4.
So this is not the same.
Here, it's in here.
But the distribution, not distribution of energy sample there. The distribution that you show on panel B.
Yeah, okay. This, this is transition state pathway. This is the inherent structure distribution. From this quenching. Okay. So this one is from the sampling. They're not the same quantity.
Yes,
So those are only the saddle points and not the minima?
These are all the lower end of these lines these are the minima, and the next one is saddle, nothing in between.
But there's just very few minima in there that
Very
are
few.
in the narrow bin on the left, and that's
Yeah.
what is confusing me.
Yeah, well, you're right. I mean, it turns out, Slinger talks about these energy landscape in terms of broad basins. You're right. In this sampling, we only have seen about 2 broad basins.
So you have that initial point of the panel 4 is are distributed according to panel B.
The initial point was picked from one of these points.
Okay.
Well, but look, on the other, at each of these,
Initial point distribution.
horizontal dash lines, and the first 2 of them sort of go through where the things
Then he
are.
says on the activation.
Yeah.
And the third, the blue one is a bit off, and the red one is way off. Now,
Right.
What were you supposed to do?
Well-
No, I think what. You're picking the initial energy from that distribution, and then saying it's not coming back.
It's activating the.
Jane gets way
I think that's right. I think that's right.
It does not belong to CCP.
Okay, that's two different. Okay.
But then, do you do many of these, picking it from the initial
No,
stage?
I didn't mention this, but the person who does this was on short leave. He was not a. So he had a finite amount of time. So we didn't do as many as we would like. The answer is no. But let me show you what we got. Okay.
Yeah.
So this is what we got. Good or bad? These points, these color symbols are the points that we got from the 4 temperature ranges. And this red curve is actually a curve drawn through these points. So the real calculation comes from these points.
The red curve is not experimental.
Not an experimental curve. This red curve.
The red curve is your experimental.
Yeah. That's the whole thing is to hope for the fact that we capture this sort of trend. All right. So but now keep in mind that we have not used anything from the experiment other than the general concept there is this inherent structure, other than the fact that there is going to be a transition state pathway that you have to sample, other than the fact that we can use linear response here. We've not used anything else. That means an output of this is we can actually predict, first of all, we can predict TG. We don't have to take TG in the experiment. And other things like, we can now go into the experiment. I'm going to the calculation and stop and look at the individual trajectories and find out what's going on during one of these big jumps. So coming back to here, we could ask, what is going on what's the difference between the atomic configuration here and here? What has changed significantly as we go into that? And we can get into details, but roughly speaking, the results are reasonable. Namely, the kind of mechanism, the kind of atomic rearrangements that take place during one of these hopping is exactly what you have. There's some cooperativity there in the way of chains. For the fragile glasses. We did the same thing again for the strong glasses. It's not so much chains anymore, it's bond swapping. So there is enough sensitivity in the details to tell you that there is some kind of a general distinction between how strong glasses behave. Strong glasses behave like network glasses. They, when you have a network and you want to move things, you basically have to do swapping. You have to break the bond, reform the bond. Bond exchange. People in the silicon, open structure, just know all about that. Whereas in the fragile glasses, like nanojunk glasses, it's chains. Okay, now I would like to ask Jim. There are also STZs at some point of rotations. And I don't think anybody, so far from what I know, in this way of looking at things, I even thought about that. So, it'd be good to speculate, where do we put the STZs? Where are the STZs in this case? Because I can easily imagine, instead of talking about glass, I can talk about amorphous solids and talk about, not as a function of temperature, I can talk about amorphous solids under deformation. Metallic glass is under deformation, and we have people who believe that what they're seeing, what they're measuring, the results of these STZs being formed, being triggered, and so there are some interesting questions there. And yeah.
No, it is very interesting that when you lower the temperature, then the surrounding, the initial state at low temperature is like very isolated in the sense that as soon as you move with your trajectory, your sample trajectory,
It
you're
goes
very
away
high
from
in
that.
energy,
Right.
very narrow.
Yes. Yeah. We can
Interpretation
talk about
of
that, but I don't have much more that I can really say with, a lot of these things we've sort of thought about, but not carefully. It's definitely worth. I would be happy to sit down and hear what you are seeing from looking at this, and then maybe continuing that discussion. So at this point, I think I'm actually pretty much close to. So let me try to get back to a stopping point. So invite more discussions. I already touched on some of this, but let me now come to the end of this. And if people want to talk more about the glass, we can. We still have a few minutes. If people want to talk about the other things, the broader things, we can do that. But at this point, I like to sort of say, well, what we just discussed is an attempt to connect a few dots. Albeit, there are a lot of open questions, but we're trying to make some connection. Focus on a problem that seems to be worthwhile. That's of general interest. Not only for the problem itself, but also in terms of implications for other systems which might behave under similar conditions. So now this is for the glass experts is to make any comment. What are the outstanding questions in terms of the fragility nature of the glass transition? Simply stated, from our point of view, all we see is that as you quench a glass-forming liquid to lower and lower temperature, you get into a very rough energy landscape, very, very deep. And as a result of its being very deep, it takes a long time for the thing to activate itself, because all you have is thermal activation, right? So, it's not at zero temperature, it's finite temperature. So this problem of the glass transition, the viscosity of transition temperature, to me is a thermal activation problem. There's no stress, supposedly because we relax everything, constant stress, zero stress. So in that framework, the fragile glass, or the fragility of the glass transition is very reasonable and rather simple. Namely, it takes time for the systems to sort of bootstrap its way out or self-organize its way out of there. And it seems to me there's nothing more beyond that. So in that context, it seemed to me, rather than focusing on the glass transition temperature, one should really focus on that crossover, which is where you go from the strong to the fragile. In that case, there may even be questions about are there additional crossovers we haven't seen at lower temperature. And also, there is speculation of a crossover in silica at higher temperature. Those things would be beyond the experimental range. Okay, so there are still things to be discussed, but it seems to me the energy landscape has got to be a sort of a central issue now. And then we can all start thinking about how do we understand these energy landscapes as they change under quenching, under stress, what have you. Okay, so and then I think it's clear. You've shown that thermodynamics are important, but this is really a matter of kinetics, transport. So kinetics means you not just care only about energy minima, you really care about activation, you care about saddle points.
But as you said, you're connecting it with the green Kubo to fluctuations. So it's a completely equilibrium correlation function.
Green Kubo, by the way, will not last when we go broader, because when we start to look at external stress of the system is going to be out. Green cobalt is really a linear.
Yes, but that's what you're doing.
That's why we're doing. We can get away with it because it's the glass problem. When we start talking about sharing the system, I think people who are actually
You're getting away with it because it's the super cool liquid problem.
Yes.
It's not the glass problem. Yeah.
Well, I don't know. Okay.
Glass is when it has fallen out of equilibrium, I think, is the sort of way people talk about it. The super cool liquid is still in equilibrium.
Right. Okay. So there are challenges both to the people who do simulation. I think we're still in need of very effective methods. Various people have this, like hyperdynamics and kinetic Monte Carlo in various forms, and everybody has their method. I think we should be open to that kind of discussion. Also, I like to throw this out to the people who have thought about the mole coupling theory. Mole coupling theory, I think Jim will say something about that. I think in your review, it comes closest to being some kind of a theory. Right. Okay. So, yeah. So, but I think there are, I don't know, the people who are actually responsible for the current modification of the mole coupling theory, and these are people like Fuchs and Cates and so on, who talked about
and Biroli and Bouchot and Bonnier.
Yeah, okay.
There are lots of people.
Yeah.
Yes.
And so instead of this mole coupling theory, there's now mole coupling theory -ITT. They call it integration through threshold.
Sri, are you going to give a talk at some point on a sub? Can you give? You might want to just. No, but you might want to give a blackboard talk on summarizing what's going on now.
So it seems like by broadening our thinking, we are challenging both the simulation community to come up with more powerful, better understood methodologies, and also the theoretical communities to come up with whether it's glass reality models or MCT modify extended, what have you, or just regular master equation network model things depending on transition state theory. So that just opens the door to many things, and this is make sure I don't forget to mention that Jim is going to talk about the glass on Thursday. This is October 16th, I think it's a Thursday. And then on Friday you will also talk about some STZ.
No, Friday. This is because you.
Yes.
Push.
Right. Yes.
Because.
And us too. We pushed you.
No, I pushed her and she pushed
It
you.
all comes about because, and my eyebrows are way up because Sid.
I would really say we don't want to get into that discussion here. This is a talk. We should just talk about the talk.
The point is
Yes.
Sid avoided his discussion about dislocations
But this is
because
good.
he obviously was impressed by my objection.
But I just want to make, right, so I think, there's you're saying people should focus on energy landscapes. They have been for many, many years in the context of the glass problem, and 3 is, right, so that's not, I don't think, but I think what you're doing with and even, this kind of idea of constructing networks and effective transition rates have been done. You're just doing it differently. And it's interesting to, I think, compare these different approaches.
Along this line, I would like to make a comment also. It reminds me a lot these experiments in granular material of intruders. You put on an intruder in your system and look at the energy you need to give to this intruder to make move to one metastable state to another.
Okay.
And the idea is that if you are able to analyze properly this rough signal that look pretty much like the signal you were showing us, rougher as you get closer to the jamming transition, then you can understand the mechanics of the whole system. I think that's probably your message. Look at one.
Right. Have you talked about it already, or can we hear more about it? My audience, jump in?
I think Michael Falk had done something in glass along this line, and Olivier Dauchot in granular, but experimentally.
You're talking about dynamical heterogeneities? No,
it's a way to probe. It's definitely a way.
You're talking about pulling.
Yeah, it's pulling, it's probing dynamical heterogeneity through the motion of one intruder. is having a crackling noise signal. It's a favorite paper a few years ago.
So, in terms of like energy landscapes and viscosity and fragility, rather, I think there is some reasonable understanding of what the correspondence is. Very sort of simply put, if you have densities of states which are very narrow, you have strong behavior, and if you have very broad densities of states of energy nearby, you have fragile behavior. And that even has been used to explain the crossover in silica, where you have sort of a truncation of the density of states at low energy end, which gives rise to this fragile strong crossover. But I think the thing that was interesting in what you spoke about, which hasn't particularly been done to satisfaction, is looking at the energy landscape in terms of minima and transition states to construct some kind of a sort of a dynamical model from which you could extract quantities like the viscosity. I didn't understand how you do it. I looked at the papers, but that kind of sort of defining a framework in which you could meaningfully calculate transport quantities from a landscape picture is an interesting thing.
I think that's what.
Can I ask a question about that? So you talked about transport. You showed us an example where you went from 1 deep minimum and then you were up at high energies for a long while and you went back down. How different were those states? If you were to look at how far you'd gotten in phase space, how far have particles needed to move to go from that 1 minimum to the next deep minimum that you sampled?
Yeah.
Are you seeing sort of single atom hops? Have all the atoms moved by their diameter? What's the?
I could show you. What we. Of course, all the information is there. You just have to pick a point. When you say how different is it from point A to point B, you just have to pick the point A and B, see how far apart they are. Then you can look at and start to compare. So we have done simple things like we marked the particles and use arrows to show their movement, displacement maps over this transition, over this period of activation, relaxation. You've seen some of those, so I can show those to you.
Okay.
Okay. We've done it.
But just as a broad sense for the group, if there was 1 minimum you started and then you were high energy for a long time and then another one. If you just look at the distance particles move between those two states, is it a large, is it 10, 1, 0.1? That's the question.
Not 10, but maybe I can use this as a way to go to the. I don't think we're going to have time to talk about this, but this is maybe along the lines which I have in mind. This is a whole together different problem. We have so.
No, I think
we should.
That's okay.
I have to go lecture.
Yeah.
I'm doing a remote lecture, so I have to.
Wow. Okay. All right.
Yeah.
But I was just hoping you had just a number in the.
I don't have those.
Yeah.
0.1, I would say.
You see very narrow changes.
It could be small.
The fraction of radius is many radius.
Okay. We could cut the argument.
I think the room actually is where we're going to be kicked out in just a minute. So maybe let's thank him and continue discussion over lunch then. Yeah, thank you for that.